And thanks. Today, the topic for today is the hyperparameter optimization of graph networks for molecular property prediction. And I know probably there are too much information in this title, but don't worry about this because I will try to make this talk easier. And today's talk have 4 parts. I will start by general level talking and to the specific level, more specific level at the end of the talk. So in the first part, I would like to show some examples of AI for scientific discovery, especially for neural networks. And in the second part, in the second section, I would like to narrow down to graph networks for scientific discovery. In this section, I will introduce what is graph networks and what is graph networks for drug discovery, and also I will introduce graph networks for molecular property prediction. And in the third part, I would like to introduce another part of our work, optimization. And in the third part, I will introduce what is hyperparameter optimization and why we need hyperparameter optimization. And finally, I will focus on our work hyperparameter optimization with graph networks for molecular property prediction. And finally, I will draw the conclusion to end today's presentation. Okay, background. I've listed some examples for AI for scientific discovery, especially neural networks, because you know AI is a big topic, so I can't list all of them. So I selected neural network related AI for scientific discovery. And you might already find the application of neural networks across many disciplines, like for example, like from the first one, physics, the second one is petroleum, and to the like protein, medicine, and drug discovery. And the final one is about material sciences. It is noted that last one is our DPRC funded manufacturing utility project. And next part, I would like to introduce a type of neural network. It is called graph network. It's quite new and advanced in neural network family. If you have already used the neural network before, and I think you definitely know deep learning can efficiently capture the heightened patterns of your blending data, right? But however, there are an increasing number of applications where data are represented in the forms of graphs. In other words, traditional neural networks are hard to directly process graph data. And before we know graph data, before I introduce what is graph data, let's see what is graph data at first. Let's see the figure 1. There are 2 figures. At the left, there is an image of cat, right? And when we process, but this image can be represented by matrix, right? And when we input them to the convolution neural networks. But however, on the right side, there are some points connected with each other. And in brief, this is graph. So in other words, graph consists of points and edges. And next, you might already know the AlexNet, or maybe you already used the AlexNet before. This is convolution neural networks. It is a traditional neural network, so it is able to process images to do image classification. And the input and at the left side is an image. It is a matrix, right? But now let's turn to the graph. At the figures in the figure 3, there's a graph data. It is a social network, right? People are the nodes, and the relation between the people are edges. And the first question is it possible for using it is possible for using AlexNet to process this graph, this social network? And I think the answer is yes, in strict. But however, you have to do a lot of additional work before you input the graph data to the AlexNet. For example, like you have to represent this social network in the matrix format or maybe vector format. And before we get in the graph network, let's see the one key component of graph networks. It is aggregation operation. This operation is very, very important in graph networks. It is used to learn the representations to capture hidden patterns. So for example, let's see the figure 4. If we want to learn the feature representation for H0, how we do that? So we collect the information from the neighbors, from the H1, from the H2, from H3, and sum up those information with H0's information to generate new feature representation for H0. And we do this operation iteratively. So we swap this operation to the whole graph for each node. This is in the first round. And in the second round, if we want to update the feature representation for the H0 again, this time H1 have already collected the information from the green nodes, right? So the information from the green nodes will pass the information to H1. And now when H0 want to update its representations, feature representations, it will collect the information again from the H1. And right now, H0 have already get the information further from the further nodes because H1 this time have already contains the partial information of both two green nodes. And this is the key component of graph networks. And then now let's see how this aggregation works in real graph networks. In real graph networks, there are two types of graph networks. The first one is called the spectrum one, and the second one is called the spatial one. And but they do have aggregation operation, but they get a different start point. For example, like the first one, spectrum one is supported with a lot of math, and the spatial one. And the spatial one is supported with, is inspired by the convolution neural networks, traditional convolution neural networks. Before we introduce what is the spectrum one, let's see this graph. There's a 6 nodes, right? And what is degree matrix? Degree matrix is a diagonal matrix. The degree of each node on the diagonal lines, right? For example, if we want to find the degree of the node 1, is 2, right? Degree, because node 1 connected with 5 and 2. If you want to check the second, the node 2, the node 2 degree is 3, right? Because node 2 connected with 3, 5, 1. So here is 3. And next, what is adjacent matrix? Adjacent matrix is a 0-1 matrix, and it is used to represent the adjacent situation. If two nodes are connected with each other, then it is recorded as 1 in the matrix. For example, if 1 and 2 they are connected, so we recorded 1 and here. And this is just symmetric matrix. So here is also 1, because this is 1, 2, 3, 4, 5, 6 node. 1, 2, 3, 4, 5. Oh, sorry. Here is 1, 2, 3, 4, 5, 6 node. So you can check this matrix to find out the adjacent situation. And so the spectrum graph networks from the KEEP is defined as this equation. So the degree matrix and the adjacent matrix are normalized, so they are tilted. And how these neural networks do. So these neural networks use degree matrix, multiply adjacent matrix, multiply degree matrix again to multiply HK. HK at the first layer, HK means input. So if you have the 5 nodes, if you have 5 atoms, so you have to give the 5 atoms properties like mass or maybe just the aromatic property. And W is the weight matrix, is learnable parameters. And when you do once, so you will get to the one feature rotation for graph, and in the matrix, every row vector is for atom. And the next part is about the spatial one. Spatial one, I think, is more intuitive and it's quite easy to understand. For example, if you want to learn the feature rotation for the node 2, so you have to collect the information from its neighbors. So n means how many neighbors. So 2 have 3 neighbors, 3, 4, 5, and 1. So you sum up the neighbors feature rotation plus itself to generate the feature rotation V. And you send V to the weight matrix with activation function to generate a new one. And you have to do this iteratively for every node. And it's noted, and here you might already find here is n, means the node only with same degree share a weight matrix. For example, node 4 with degree 3 and node 2 with degree 3 as well. So they share one weight matrix, but 6 with degree 1. So 6 has their own matrix, weight matrix. And this is all about graph neural networks. And now let's get some relaxed content. What is graph neural networks for drug discovery? Because we have already know what is graph neural network. And the diagram shows the process for the drug discovery from targets to lead discovery, lead optimization, preclinical study, and to the clinic trial. And during this process, there are 3 main aspects for graph neural networks application. The first one is called the molecular property prediction. The second one is molecular design and optimization. The last one is virtual synthesis prediction. And the advantage of applying graph neural networks for drug discovery is time saving. It's absolutely because graph neural networks is cheaper than DFT, right? Because DFT is time consuming. And our research focused on the graph neural networks for molecular property prediction. So we summarized this framework. This is framework for molecular for graph neural networks for molecular property prediction. In this framework, there are 2 main parts. The first part is called the graph layer. The second part is called the task-specific layer. So the input is a molecular, right? When we input the molecular to the graph layer, the first things we need to do is called aggregation. So that we have already introduced what is aggregation, right? So if you want to learn the representation for this carbon, you have to collect the information from the nitrogen and oxygen and this carbon to here in the first layer, right? And how many times you do the aggregation, it means you have how many graph layers. Because in the second graph layer, when you do the second aggregation, the information from at here from this carbon will be passed to this nitrogen, and the nitrogen will be passed again to this carbon. So in the second layer, this carbon collected the further information from the further nodes, from further atoms. And after a lot of graph layer, you will get the matrix at here. So this matrix is called the feature representation, and each row vector is for every atom. For example, the first row is for maybe just the oxygen. Second row maybe just for this carbon. And after that, after you get the feature representation, you can do a lot of work. You can do a lot of tasks. It depends on your real situation. So in our case, we need to predict the molecular property. So we have to molecular property prediction is a graph level task. So we have to collapse the matrix into the vector so that we can input the vector to the fully connected layer. So we call this task specific layer, and to make the prediction for the molecular property. And even we divide these two parts, we divide into the two parts, graph layer and task specific layer. But in real situations, they are connected with each other to ensure propagation works well. And now let's get in the next section, hyperparameter optimization. So what is hyperparameter optimization? Hyperparameter optimization is a problem of choosing a set of optimal hyperparameters. For example, like optimizer, learning range, how many layers, like how many graph layers we introduced before, and maybe how many, the size of each layer also. And a hyperparameter is a parameter whose value is used to control the learning process. And so in brief, a hyperparameter will not be changed during the backpropagation, right? Because a hyperparameter is used to control the learning process. But however, deep learning algorithms are very sensitive to many hyperparameters. And from our perspective, graph networks might face more challenging HPO problems as irregular data structure, because in previously graph networks, convolution networks is used to process irregular data like images. They are the the layout of pixels are regular, but however, graph data like moleculars, I mean social networks and transportation networks, citation networks, they are irregular. So we might need to more complex neural architecture to deal with this kind of data. And this is more formal definition of hyperparameter optimization. So, but there are too much details due to the time limitation, so we just skip the limitation. And anyways, the goal of the hyperparameter optimization is to find the lambda, to find the best hyperparameter settings, which can give us the expected lowest error here. And the process of looking for best hyperparameters, we only use the training data and valid data set. In other words, we get the test data set away. So keep the test data away in case data leaking, information leaking. And why we need hyperparameter optimization? Because hyperparameter optimization can improve the performance of machine learning algorithms. So it's not just about the graph networks. And also, hyperparameter optimization can improve the reproducibility and the fairness of scientific studies. And automated HPO is clearly more reproducible than manual search, because previously people used to do manual search to check the hyperparameters to find the appropriate set of settings, and direct impediments to select appropriate hyperparameters to achieve satisfactory performance with lower computational cost. Because, as you know, the training of neural networks, especially deep neural networks, it takes a long time, like 3 days or a week. If you And every time you want to check the hyperparameter, a set of hyperparameter settings, you have to, it means you probably need to run this model a week to check one solution. If you want to check 100 solution, you need probably 100 days. And now let's back to our work, graph networks with hyperparameter optimization in molecular property prediction. In our research, there are quite a lot of graph networks, but we selected the neural fingerprint. It is also called the GCN, because this model has been proposed with chemical background. And the hyperparameter optimization approach we focused on, including random search, CMA-ES, TPE, HiSCA. We proposed the HiSCA method and also HiSCA with TSM. And HiSCA is a genetic algorithm. It is called the genetic algorithm with hierarchical evolution strategy. And the dataset we used in our research, ES-OL, first solve, and lipophilicity. So those three datasets have different target tasks. So ES-OL is to predict the water solubility. First solve is used to predict hydrogen-free energy, and lipophilicity is used to predict measured octanol water distribution coefficient. And as the input in our research, it is called SMILES. I think in last talk, the speaker have already introduced what is a SMILES. SMILES is just like lifestyle encoding for a molecular, and we can use the RDKit library, Python library, to use this Python library to generate the corresponding molecular graph like this. And after we generate the molecular graph, so we also use some features for each atom, like chemical element, degree, aromatic, radical, electrons, and etc. And now let me just in general level to introduce 3 or 4 HPO methods. The first one is random search. I think this is the most easy one. So random search is brute force. And if you have 4 hyperparameters needed to adjust, so you just need a 4 uniform distribution. And every time you just make sampling from 4 independent unit for distributions. And after you get the hyperparameters, like lambda, you bring the lambda to the model and you just check and find the loops, and then you record the loops in a list, and finally you can like sort the list to find the best hyperparameters. This is random search, and the random search is considered as a baseline for all HPO methods in deep learning. And the next one is called the TPE. Is the core of this approach is this approach is aims to build the model for the 2 groups of hyperparameters, like from here. We call the red points observations a good group, and we also call the blue points with they are bad observations, so they are a group. So TPE will build the model for these 2 groups of data, like LX and GX. And the next sampling, next hyperparameters likely to be drawn from this group. So this is the core of TPE algorithms. And next one is called the CMA-ES. CMA-ES is evolutionary computation, and the core of CMA-ES approach. This method is to maintain a multivariant normal distribution, right? Like if you have 4 hyperparameters, so it means you have 4-dimension multivariant normal distributions, and every time you find some observations and you check the hyperparameters, so it means you own the historical information, and the CMA-ES will update the distributions to support the next decision. And this is our method, hierarchical evolution strategy, genetic algorithms. So, and I believe you already know the genetic algorithm in last talk. So every time we start from the population, so population will be sent to the fast evaluation at first in order to check in order to save time, and only the best solutions hyperparameters will be selected to do full evaluation. The main difference between the fast evaluation and full evaluation is if we set the total epoch as 100, so in fast evaluation we'll only run like 20 or maybe 30% of total epochs, but full evaluation will run all epochs to check the hyperparameters. And then the best hyperparameters will be stored in here. And for the next generation, we will randomly select one parent from here to here as parent 1. And the next parent is selected from the last population to here in order to ensure diversity. And now let's see some of our experimental results. This table shows the results on the ESOL dataset for comparing our method HiSCA with Bayesian optimization and traditional hyperparameter optimization method. So our method shows better performance, right? We use the root mean square error as criteria. So lower value means better. And also here defined the search space. And this table shows our work for exploring which hyperparameter methods is better. So this table shows a general experimental setting on lipophilicity dataset for random search, TPE, and CMA-ES. And we find that the TPE outperforms than random search and CMA-ES. But we still believe the work of exploring the efficiency, the performance of CMA-ES is deserving, because probably when we give more epochs, CMA-ES will be probably better than TPE, because CMA-ES is a revolutionary computation. Generally, it need quite a long time, relatively long time. And the last table shows our recent work is because we thought hyperparameter optimization is expensive tasks, so we don't want to optimize all hyperparameters. So we are trying to figure out optimizing which hyperparameters can give us more benefits. So we group hyperparameters in hyperparameters from graph layer, hyperparameters from task-specific layer, and here is fully connected layer, and also both of them. And we find that within same computational cost, even the search space for last column is large than the first and the second column. But optimizing both graph and fully connected layer hyperparameters can give us best performance, right? And last one. We believe HPO for GNN molecular property problem is helpful for improve the performance. And from our experience, TP shows advantages over the HPO methods given relatively limited computational resources. And we find in those three datasets, HPO for hyperparameters in both graph layers and task-specific layer could gain more benefits. And we also believe within the increasing number of advanced GNNs and HPO techniques emerging, the study of combination of GNN with HPO is significant. And that's all for today. Any questions?